All right, so this is question 2.6 and it's called Palindrome. And for this question, we want to implement a function to check if a linked list is a palindrome. So test case I just provided here was we have a linked list that says 1, then 2, then 3, then 0, 3, 2, 1. And so this is in fact a palindrome because if we read it forwards, it's the exact same as if you read it backwards. That's the definition of a palindrome. And so if we read it 1, 2, 3, 0, 3, 2, 1, and if we read it backwards 1, 2, 3, 0, 3, 2, 1. Great. So to do this, I just quickly created 7 nodes here to implement this linked list, and then I just linked them all together by setting, their next nodes. And this is done just using a simple node class where we pass in the value that's stored within the node, and then we just simply have a pointer to the next node. So we then have our palindrome method, which will be returning a Boolean because we want to return, whether or not it is in fact a palindrome. And we're just passing in node 1, which is the head of the node, or head of the linked list, and that is this first number 1 here. Simple enough. So the first step for this is if the head is null, we just want to return false because, it's not a palindrome if, we're just dealing with a null linked list. So let's return false here. And so what we want to do for this algorithm is we're going to use a stack, right? And so we're going to push to our stack all the way up to the middle of our linked list. And so if we have an odd number, an odd length, if we have an odd length linked list, which in this case, this has a length of 7, and so we're only going to push to our stack the first 3 nodes here, and we're going to ignore the middle one. And that's because, we don't really have to concern ourselves with the middle node when we're dealing with a palindrome, like it's kind of symmetrical that way. And if we had an odd number, or an even number, sorry, like this, then you don't have a middle number, and so you still just, push to the stack the first 3 nodes in our list. So to do that, we kind of have the problem of, okay, well, how do we only push up to the middle of our linked list? And to do this, we're going to use I think they call it the fast and slow pointer technique, and that's used to find our midpoint. And this is done by having one pointer that moves each time when we increment it, it's going to move 2 places. So the fast pointer, we'll call it F here. Why don't we just move this ahead some? So the fast pointer will go 1, then 3, then 3, then 1. But we're going to have just a slow pointer, or a normal speed pointer, that just iterates by 1 each time. So 1, 2, 3, 4, etc. And so what that allows us to do is find our midpoint. So they're initially both set here, and then this one increments to 3. This increments just to 2 because it only increments once. This then increments to the next 3. This one increments once here, 2, 3. And then this one increments all the way to 1. Then this one increments to 0, and it's finished because the next value here is going to be null. So just like that, our slow pointer was able to end just at the midpoint when the fast pointer hits the end of our list. So that's kind of how you find the midpoint. And what this enables us to do is we're going to push to our stack with every iteration of the slow pointer. So I'll show that again, just to kind of see what it looks like visually. Is we're first both at 1, the fast pointer increments by 2, and then slow pointer increments by 1. And we do push the first value, of course, so it's 1, and then we push the value of 2, and then the fast pointer increments by 2 again. We then push the third value, or the value 3, which is also the third value, and then we increment by 2, which is 1, and we increment again by 1. But at this point, since it's kind of reached the end of our list, since, fast.next, I can't spell, is equal to null, then we're not going to append to our hash set, or our stack here. And so that's kind of how we get the first 3 numbers into our stack. And so as we're reading, the following parts of our list, we're just going to hopefully, pop these off the stack in the correct order, and if we're not popping, say if this is equal to 2 and doesn't equal the top of our stack, then we return false because it's not symmetrical, it's not a palindrome. So let's go ahead and implement that. So we're going to have a pointer called, let's call it slow pointer. And we're going to have another pointer called fast pointer. Oh, and these are not going to be equal to null. They're going to be equal to the first node in our list. And then we need our stack. And we're going to be a stack of integers since we're pushing their values. And that's what we want to compare. So we'll call it stack equals new stack. And I just want to make sure that I imported it. Yep, I imported it earlier. And so what we want to do is find the midpoint and push all the first half of values to our stack. So while the fast pointer does not equal null and the fast pointer dot next does not equal null, because we're going to be iterating by 2, and the last thing that we want is this to be null and then try and do a dot next on it, because that'll error our program. So we will then push to our stack dot push the slow pointer dot data, because that's what I defined here to store the node's value or their data value. And then we just increment our slow pointer by 1. And then we're going to increment our fast pointer 2 times. Great. And so now, one thing that we have to take care of, and this was the tricky part for me when I was dealing with it, was we need to ignore, if we have an odd length, this middle number here. And so, but if we have an even length, we don't want to ignore this value because, well, there's no middle number here, so we have nothing to ignore. We just care about it if there is a odd number. So if fast pointer does not equal null, then we do fast pointer equals fast, or no, this is the slow pointer. If fast pointer does not equal null, then slow pointer equals slow pointer dot next. And so that's because if this does not equal null, then it is an uneven number, because this will be incrementing by 2 each time. And so that means that if it was null here, then it is even, otherwise, it's even. But if it is null, not null here, then it's odd. And that's because this is incrementing by 2 each time. And so if it were null at this point, then we have a even number. But if it was null at fast pointer dot next, which it would be in this case, if fast pointer dot next, we could also say this, is equal to null, then it's an odd number, and so we have to increment our slow pointer 1 extra time to just kind of skip over this middle value here, because we don't want to push that to our stack, and we don't want to try to pop this value from our stack because it doesn't have to match, you know, the top of our stack. Great, so let's move on to popping it off. So while the slope pointer does not equal null, so we're going to iterate through the full length of our, or the remaining length of our list. So if our stack, the top of our stack, so we're going to peek the top of our stack, does not equal the data stored in our current slope pointer, then clearly it is not a palindrome because they need to match. So we're going to return false. And otherwise, we just iterate through our linked list as usual. Great, and so what this is doing is just that we're checking so that if we have our hash set here of 1, 2, 3, at this point we would be pointing to this value here. We say, okay, is 3 equal to the top of our stack? We'd be peeking this and go, yep, it is. So we iterate to the next one, we check, we say, okay, yep, it does equal this one, so we pop this off our stack, and etc. But say if this was the value of 4, and our stack is 1, 2, 3, then we see, okay, is 4 equal to the top of our stack? And since it isn't, right, we would then look at this line of code and say, okay, it doesn't equal it, so we're going to return false because it's not a palindrome. And I just quickly forgot here, we just need to pop our stack, because since it does equal the top of our stack, we want to pop it each time and just iterate to the next point or the next node in our list. So finally, if we were able to iterate through the entirety of the list and pop all the values off and they're all equal to each other, we then just simply return true. And that's the end of our algorithm. So let's go ahead and run this here. And just as a reminder, this is 1, 2, 3, 3, 2, 1, which is in fact a palindrome. Great, and return true. Well, let's say we change it to 4 here. And so it error out at this point here since 3 cannot pop off, since 4 won't pop off 3 from our stack. Great, and return false. And you know, if we passed a null one in here, like a null head, so just do that, it'll also return false. Great, and false. So the complexity of this algorithm is O of n, because we're just iterating through the length of our list one time. We iterate, you know, halfway at this point, we iterate through the other half here. And now the space complexity is like O of n is 1/2 of n, where n is the number of nodes in our list. And that's because we're just, you know, pushing to our stack, you know, half of the numbers. But we should just look at this as O of n, since we don't really care about this division. So I hope that helped, and I hope you guys have a great day. Thank you.